My question today is, what is an object really? Like anybody could actually answer that question. Well, I'm going to have a go. The first part of my answer is, you can all read, sorry. That was a guy called Peter Landon. He was one of the original authors of the Algol 60 spec in 1960. He invented blocks by indent, think Python, YAML, and CoffeeScript. And he coined the term syntactic sugar in 1964. He died in 2009, age 78. This slide kind of corresponds to my talk, because the last few years I've been writing code and noticing things, and I thought I was being really original until I had the misfortune of being sent a book called Let's Over Lambda. Or maybe it was a stroke of really good fortune, because that led me to do a bunch of reading on Lisp and Smalltalk. And in a bunch of papers written in 1960-something, I found all the stuff that I thought would be really original about. So yeah, so much for that idea. Anyway, here's a picture of me when I was younger and more handsome. No, that can't be right. Wait, maybe I'll put it on the slide. No, in fact, this is a picture of me when I first encountered object-oriented programming. No, it's different this year. I did, in fact, bring my chocolates. Here they are. Good quality chocolates. Life is too short to eat bad chocolate. And if you want one of these, you will tell me the name of the character. Just shout. He was first.
Maximus.
That's right. Close. I've got to open these. Of course, it's childhood, so I can't open it. Sorry. Please pass on. Alright, so here's the rules. Judge's decision, that's me, is final. Please be nice, no more than one chocolate each. So it was Turbo Pascal that turned me into a horse. A puzzle horse. I managed to get my head around all the definitions of everything, and the weird fact that a string of 5 characters is different to a string of 8 characters. And the records were okay. The whole procedure function thing sent me down the wrong road for many years. But overall, it wasn't too hard. Right up until I hit these object things. Constructors, methods, private, public, protected, destructors. Virtual methods, virtual destructors. Beams, animals, darkness. Just shout.
Counted tone.
I think he was first. Okay, Rory had his hand up. I don't know if that means he knows the answer.
Counted tone.
Yeah, Jugig thought. Sorry. Who said Jugig thought first? Yeah. Was it him? Okay. Right this time. So objects at this point seemed like a very complicated way of winning Castle Dungeon. So at this point, it's pretty clear that the answer to my question is a thing that turns me into a puzzle horse and makes me laugh like Jugig thought. At about the same time that I was learning Turbo Pascal, Lisp and Prolog were being taught in my computer science classes. Notice that I say I taught, not I learned. Have I lost vocal here? You guys all hearing the microphone? Okay, yeah. Okay. So they were being taught in my computer science classes, but I can't say I learned because I regarded these things as strange experiments in syntax, and I wondered why on earth would anybody want to write working code with these bizarre contraptions. That's the movie. I'm going to have to be eating a lot of chocolates here. Come on, guys. Oh, nice try. That is in fact Scuttle from The Little Mermaid. Bonus sweetie. What is the name of the object he is holding? No, sorry, no. That's it. Who said Dinglehopper? Well done. I'm getting better at this. So that's Dinglehopper. If you want to know what it does, you're going to have to watch the movie. I'm not going to explain. At this point, without knowing it, I had become used to an imperative approach to programming, which can be inaccurately summarized as repeatedly putting different values into the same memory location. So that first example there is, in fact, a a side effect-free imperative compound statement in C. The Ruby equivalent is just below it, which is arguably less imperative and definitely less noisy. And that bottom one is machine code. Well, actually, it's assembly language, which is one step up from machine code. Look, let's face it. Computer languages exist so that humans find it possible to write software. Because the CPU doesn't care if you have nicely lexically scoped variables or if you have a bunch of globals. The CPU doesn't care if your integer counter rolls over to 0. And this applies to a lot of things that we regard as good practices. The CPU doesn't care as long as it's got code to execute. The CPU only cares if you tell it to execute the wrong instruction or a non-instruction, or if you try and access a non-existent memory location. And there's probably a couple other things that I've forgotten, but it doesn't care very much. It only cares just enough to do that. That's the movie? No, that's the actor. Almost. I think I'm going to have to hand out things for almost. That's the movie. That's right. Who said Stanley Ipkiss? And the guy in the red over there. Because I'm the judge after all. I can decide to give out 2 sweeties. So higher level languages were progressive attempts to make it easier for humans to write software and attempts to prevent developers from doing that to the CPU. Meanwhile, in a different universe, since about the 1930s, work on formalizing algorithms had been going on using Turing machines, lambda calculus, and some other math frameworks, which are actually, when you think about it, just as hard to use for reasoning about software as machine code is. Okay, so this is a representation of a magnetic field. But instead of calling it N and S for north and south as the poles, I've called them lambda and that thing. It's not, is it phi? Okay, well, I was looking for something that kind of put a 1 and a 0 on top of each other. And that's actually a symbol from APL, so I figured it kind of worked there because that's the sort of machine code pole. That's the actual execution pole, whereas lambda is for sort of pure maths. Say what? It's all Greek, yeah, it's all Greek. You're right, I can't disagree with you on that one. So I read somewhere that these poles started off very far apart. You know, you've got machine code over here, the actual bytes or the punch cards to go further back. And on this end, you've got pure lambda or pure maths. And ever since then, they've been converging very slowly. And the side effect, that's a joke, you don't have to laugh. Okay, no more geek jokes, bad. All right, the side effect of this convergence has been that it is easier for you guys to keep your thoughts in sync with what you see on your editor, and for me too, because I write code, naturally. That's the side effect of this convergence. Lisp programmers, you see, that is why Lisp never caught on, because saying Lisp programmers is a pain in the posterior. Let's just call them people who write Lisp. We'll say somewhat condescendingly that all languages are becoming more like Lisp. And I have to say they may have a point. Anyway. So the next part of the answer to my question is, objects are things that help you think about writing programs. I like to look at this a little bit from the pure maths point of view. Numbers are actually really strange things. Has anybody here seen a number recently? Nobody? I'll settle for taste, touch, smell, hear. I'll settle for ever. Has anybody seen a number ever? No? Okay, what's that then? Oh, yeah, we're getting it. That's even closer. Yeah, in fact, it's my hand with my thumb folded and my fingers, also known as digits, extended. So you could say, to stretch a point, that this is a digital representation of the number whose spoken representation is 4. And unfortunately, English makes my point a little bit harder here because there are several words that sound like 4, but we use context to disambiguate. Like if I did this in a restaurant, you can be pretty sure that nobody's going to have to duck because a little white ball is going to come flying in. All right, that was a golf joke, and I haven't played golf for longer than I've been programming. Where was I? Right, okay, so there's a good reason that nobody has seen neither hide nor hair of a number, and that reason is that numbers are not hairy. And there is a good reason that numbers are not hairy, and that is that they do not exist in this world. They exist in a world called the University of Discworld. I knew I was going to get that wrong, which is why I did that. They exist in a world that mathematicians call the universe of discourse. So numbers come into existence in the universe of discourse when you count things. So 1, 2, 3, 4, 5, 6. It's going to take far too long. Call it 144. And all of a sudden, in the universe of discourse, there exists a set of counting numbers. I'll call it the house of counting numbers, and the house of Rubyfuza 2014 attendees, because you guys are a set. And at the same time, so basically, whenever you count something, you create two sets. You create the set of numbers, because one number by itself makes no sense. And you create the set of things that you're counting. So, a flock of birds, herd of cows in a field, pigs. Herd of pigs? It's a herd of pigs, isn't it? Flock of geese. So let's say you had 5 pigs and 7 geese. And you know that you have 5 pigs and 7 geese because you are a very literate swineherd. Maybe that's numerate. So would you now be a very famous literate swineherd because you have 12 flying pigs? No, definitely not. Because there are different kinds of things. There are different types. I suppose you could say you have 12 animals, but that leads us down the slippery slope to taxonomies, and I might have time for that later. So, along with the other houses in the universe of discourse, do I have to go over them again? Pigs, cows, geese, all those things, We have just created the house of type. There's a set of things which are called types. So let me look at type from a machine code point of view. A type is basically a binary format. In other words, how do I get instances of this type into memory? It's a value space, which is the values that I can store in here, which can be summarized for integers, 32-bit integers, as the smallest and the largest. Floats you can store minus infinity, infinity, 0, minus 0, not a number, and some other things. And types are used. Oh, and one other thing, there are a set of operations. Obviously, that's not all the operations that I can perform on integers in 32, but it gives you the idea. And types are used in programming languages to prevent you from applying operations to the wrong kinds of things. For example, if you try to take the binary representation of a particular integer and add it to the binary representation of a particular float, you'd get garbage because their representations are different. For starters, the one's 32-bit and the other one is, 64-bit, 80-bit, 128-bit, whatever it is. In case you're so you have to convert an integer to a float before you can do an operation on it, which is one of the things that we do with types. In case you're wondering, this is where the coerce method in Ruby fits in, but that's mostly just an aside. On the lambda pole, remember the lambda pole and the phi pole, or the APL pole? On the lambda pole, the type is quite similar to this. Obviously, there's no binary format because it's an abstraction. It doesn't exist, just like numbers don't exist. And there is the value space, the set of counting numbers, the set of integers, the set of rational numbers, the set of real numbers, all that kind of stuff. And there is the set of operations that you can apply to it. I mean, this is a bit harder to make because up until a few hundred years ago, you couldn't get the square root of -1. It was garbage. These days you can. It's called a complex number. And that happened, fairly recently, actually. So that's the next part of the answer to my question. An object fills the role of an instance of a type. Think the number 5 in Ruby. The number 5, or 5 plus 7 in Ruby, you've got an instance, an operation, and another instance. Okay, it's all pretty obvious so far. So an object fills the role of the instance of a type. It also creates a bridge between the lambda pole and the machine code pole, because that means that we can think about the stuff that we're doing in terms that are more natural to us. Okay, it's a bit closer to the maths pole, which is quite hard to think about, but it's not so close to the machine code pole. You don't have to convert an integer to a float, for example. In Ruby, you just say 3 plus pi, or math colon pi, and it'll automatically say, oh, hang on a second, he's adding an int and a float, let's convert the integer to a float, and then do the operation, and everything works nicely. So it helps you think about programs. And if an object fulfills the role of an instance of a type, is there something that fulfills the role of the type itself? Well, yes, there is. It's called a class. Okay, sorry, this next slide is unfortunately chocolate-free because you've seen them already. But this brings me to the most horse-puzzling thing about object-oriented programming, and that is, how is a class also an instance? Well, the quick answer to that is that in Ruby, everything is an instance. Well, except for keywords and one or two other things, but I'm talking really softly here, so just pretend. All right, so the longer answer is we have to go back to University of Discourse. The house of bird, the house of cow, the house of counting numbers, all of those things. think about it from this point of view. Every word is a house. So every word denotes a type, which is also a set, or a value space, which is kind of the same thing in this context. This is kind of a bit puzzling, so I'll give you an example. The word cow, think that slide from just now, Brendan's slide. The word cow means all of those things. The one standing in the field, you know. Those things. The word cow means all of those. The mistake we normally make is to confuse or to munch together the idea of a cow with an actual cow. They are different things. This has in fact got a name. It's called the reification fallacy, and we do it a lot. We treat abstraction as a real thing. I said that already, didn't I? Yeah. Okay. So I'm talking about cows and reification fallacy. What does this have to do with classes being instances? Well, if I wanted to bring Daisy, but the hotel wouldn't let me, so I'd have to pretend that next to me is standing Daisy. Daisy takes up space in the real world, and an instance takes up space in memory. The idea of cow takes up no space. The idea of the set of counting numbers takes up no space, and the elements of the set of counting numbers takes up no space. So, to the extent that a class is something that takes up space in memory, it's something that can be manipulated at runtime. You can create more of it at runtime. It is an instance. It's also called a first-class citizen. So anything the language is the first-class citizen basically does all of those things. In this example, capital F float is an instance of capital C class. And numbers, well, floating point numbers, are instances of capital F float. And the confusion between class and instance is not cleared up by the fact that we habitually say things like, I'm going to invoke this method on that instance, or on that object. So there's two things that are going on there. The one is that instances don't really have methods, classes do. Okay, I'll talk about that a little bit more later. And the other thing is that we use the word object to sometimes refer to instance, to sometimes refer to class, and sometimes to refer to things that don't exist. Like in C++, a class is a compile time entity. It doesn't exist at runtime. We use context to disambiguate. Okay, what exactly do we mean by this usage of the word object? Well, in this case, it's an instance, or in this case, it's a class. So I know you guys are tummy full, eyes closed, and I'm sure there's going to be at least one nap attack during my talk. So I've put together some examples to hopefully keep you awake. What I'm trying to do here is show you how an instance of capital C class is just an instance. First 3 lines, I'm assigning it. Now, this is all working code. You can put it into a REPL or execute it. It'll work. The second one, I'm assigning it. Okay, I'm reassigning it. I'll get a constant redefinition warning, but that's not really relevant. Oh, sorry, I'm cloning it. The third one, this pig equals object. And I've said this is just unfair because if you know Ruby well, then that will make sense. If you don't know Ruby, this is like, what is going on here? So I'm actually assigning a class which is by convention assigned to a constant to just an ordinary instance. So again, the point here is that I'm treating instances of capital C class as just ordinary old instances. And that's the next part of the answer to my question. At the machine code pole, a class is a place to store operations which belong to its instances. It's also a namespace to separate its operations from operations belonging to another instance. And it's also a factory to create more instances. Because unlike in the real world where things just happen, I mean, you don't create, well, let me just not go there, that's going to get too confusing, and I'm ad-libbing, so I'll just stick to the script here. It also does other possibly not useful things, like testing if the house of object can fly across the universe of discourse. Okay, that wasn't a joke because nobody laughed. That was, though. All right, operations, also known as functions, methods, procedures, subroutines. Have I left anything out? No? Okay, slight but significant variations, meaning a function is not exactly the same as a method. All of those things result in a binary representation of the elements of the set of integers which has the spoken representation, 12. Yes, I'm beating this representation thing to death here. They don't all do it the same way, but I think you can see that there's a correspondence between instances taking a method call with a single operand and functions taking what was the instance as its first parameter and what was the operand as its second parameter. They kind of do the same thing, which is kind of possibly a little bit more obvious with that example. You can see there's a function taking a string, and in the second one, the string has a method. They do the same thing as just something else going on behind the scenes here. So that's the next part of the answer to my question. When an instance is created, it's almost as if you have a bunch of functions defined in the class which take as their first parameter an instance. And when the instance is created, all of those functions are partially applied. Okay, you need to know a bit of functional programming to do this, but they get partially applied. The instance is bound to the function, the partially applied function, and it takes whatever other parameters are left. Okay, that's hard, and I went through it pretty quickly. But hopefully, those of you who attended the functional workshops will understand what I'm talking about here. I don't know about you, but for me, that creates a nice distinction between methods being defined in the class, but invoked on the instance. So the definitions of the things don't have a self associated with them. The self has to be bound into them, and then when you have an instance and you execute a method, it has self as part of its binding or as part of its partial application or whatever you want to call it. Of course, that isn't really what happens. That doesn't actually happen when you create an instance. It doesn't bind a bunch of methods. It dispatches methods in a different way. And there are other ways to do this, and here is one of those. I can't take credit for this because I found it on the net and hacked on it a bit. That is Ruby. And it's a bit weird, not least because in Ruby you can't call an object directly. You can only execute a method on an instance. You can kind of fudge it with these square brackets over here, which makes it a little bit look like a hash operation, which is a mapping, which is actually a function. But I don't think this is going to catch on as idiomatic Ruby anytime soon. So the point here is that there's a correspondence, and the maths term for that is an isomorphism, but please don't ask me to write a proof for that because I can't. Between functions and instances. So there's an isomorphism or a correspondence between functions and instances. Over here, I'm calling a function, which I happen to have labeled rational, with 2 parameters, which returns me another function, which I've called myself here just to kind of make a point. And I've assigned that to instance out here. So instance is actually a function. It's a lambda. And when I pass that a symbol, I'm calling it over here, and it comes out, and that's basically the method that I'm trying to execute. So this function is actually object dispatch. It's instance dispatch, method dispatch. Okay, and interestingly, this is what early versions of Smalltalk did. I think this was around Smalltalk 72. Alan Kay was basically the guy who invented Smalltalk. So to eval a program list was to use one of those weird Lisp-ish bracketed things. You pass the control to the first object, and the remainder is used as message. And pass the rest of the parameters in. Like I said, this is also what Lisp does. That's a Lisp-style function execution, or a function call. So there's a very close correspondence between those. Does anybody else want some more time to look at those? I take it that's a no. All right, moving on. Some languages do make objects directly callable. I'm thinking C++ here and Python. They both use parenthesis as the call or as the call operator. I'm sure there are others. I suspect CoffeeScript can probably do this, but I didn't check. Does anybody know? CoffeeScript, can you call an instance of an object? No? Okay, sort of. Okay. I'll get back to that, don't go any further. You'll break my talk if you go further. Does anybody know if in Smalltalk you can call an instance of an object? Okay, I'll take that as I don't know. I'd be curious to know because I don't actually know. The reason I'm mentioning that is because apparently by the time Smalltalk 80 came around, dispatch, in other words, that thing over there, had become part of the virtual machine for performance reasons, so you couldn't access it anymore. Okay, so I'll come back to callable objects in a bit. From what I've seen,
object orientation is really good at implementing or at modeling implementation concepts. You know, string, fixed num, hash, array, those kind of things. It tends to kind of stop working when we get to modeling real-world concepts, and we call this domain modeling. And that might be because classes aren't very good at modeling domain objects or concepts in the domain, or it might be because humans don't use classes well to model the domain, or maybe it's just this human who doesn't use classes well to model the domain. I'm still not clear on that. They're still useful, but us humans tend to slide between various levels of abstraction. In a sense, we commit that reification fallacy recursively or maybe iteratively. But we can use context to disambiguate. Close. Kevin, yes, he said it first. That is Kevin. And you're missing some context here. The context is that Gru walks in going, simmer down, simmer down. Hey, looking good, Kevin. How you doing, Billy Bob? You can go and watch the movie if you don't believe me. But yeah, that one is Kevin. So we're missing context. Sometimes I think that the premise of object-oriented design is that once you have modeled the domain completely, all of the operations should come out and naturally be obvious and should just work. But from what I've seen, we tend to model objects in terms of what is this thing, and in consequence, what needs to be done with them kind of gets backgrounded, and it stops working so well. Okay, this is a bit of context. You guys all know XKCD, I'm sure. If you don't, it's fine. I'll go and look at XKCD when local news gets too depressing. All right, so that whole thing that I said just now about how we tend to model objects in terms of what it is, instead of modeling it in terms of what we need to do with it, is a little bit like telling a hungry person that a chicken is a kind of a dinosaur instead of explaining how to cook it. Certainly I've struggled with that. What? Cooking dinosaurs? No, I've struggled with domain modeling. I come across these things that don't seem to want to fit well as operations on any particular instance. Eventually, I realized that I was doing transformations. Close. Come on, I want to give a sweetie away. This sweetie wants to go flying across the room. The witch. Okay, who said that? Thank you. Yeah, she's just called the witch. She doesn't actually have a name. Anyway, she has modeled a transformation. She's modeled a spell, and the reification of that spell is the pi, and it works equally well to transform Mordu, Eleanor, and the boys into bears. If you haven't seen the movie, you're missing a lot of context here. Sorry about that. So you need to have kids like me, then I get to watch kids' movies all the time. Well, that's my excuse anyway. What's the movie? Oh, thank you. The movie is Brave. So modeling transformations directly means sending an object through one or many transformation stages, and it comes out the other end as something else. Yes, who said Kevin? Why isn't it Kevin? Sorry, watch it, sorry. Please pass that chocolate on. Why isn't it Kevin? Because he's got double glasses. Yeah. Kevin's got one, yeah. I did some research on this. He calls him Kevin. He comes walking down the line and goes, Kevin, ugh. And when I went and looked, so either Kevin has now got two eyes, which is kind of weird because he's not, or there's two of them called Kevin, or there's a continuity goof. I don't know. If anybody has the answer, please tell me. My kids would love to know. So this is also what functions are all about. What? Functions are mindless, indestructible, killing machines. No, definitely not. Functions are about transformation. In fact, if you look at the maths definition of a function, it's a transformation from an element of one domain into an element of another domain, and then it might be the same domain. That's maths for you. That's why it's hard to think about programs with. So that's the answer to the next part of sorry, let me try that again. That's the next part of the answer to my question. Domain objects are not very good at modeling transformations, but functions are. Okay, so here are some objects that do transformations. They all do some expensive setup stuff. You have to imagine that like you had to imagine Daisy. Lots of expensive setup, lots of CPU cycles, and they all have a exec or invoke or apply or do it or whatever method you want to call it. I mean, in this case, it's proceed, search, and invoke. But they all give back something else. So they do a transformation, basically. You give it something here on this person, and you get back a representation of a bear. Okay, so I promised that I'd come back to callable objects. And worker is basically a callable object, even though you can't call you can't have it here. Magic word non-stumbling stuff. Okay. An instance of the class of worker has this toproc. Well, the class has the toproc. And when you call toproc, you get back a lambda, which is an executable thing. So you can treat an instance of an object in Ruby as a callable thing, even though you can't call it directly. And you can see over here, I'm passing an instance of that worker. Okay, oh dear, I took factory for worker out and I renamed him as valued employee. Okay, so I'm basically passing an instance of worker in to various methods here that are expecting a block, a lambda. And that happens via the ampersand operator, which calls toproc, which gets back the lambda and passes that into the method. You could also think of this, and I'm going back to functional here, you could also think of this as a partially applied function, where the original function takes args along with payload, and the partially applied function takes only payload. That's what partial application does. And that is the next part of the answer to my question, which is that, well, there's two parts really. An instance can behave like a function, and it can behave like a partially applied function. Okay, I see some puzzled looks. So think about that for a while. I'll have questions later, and you can throw brickbats at me or whatever you feel like. Preferably chocolates, but you probably didn't bring any nice ones. So. Grog, yep, that's right. I've got a lot of sweeties left. Bonus points. What movie? You said it first. Okay, so that's Grog from the Crew. It's trying out an untested idea. I've always been a little bit leery of MVC. And I've never really been able to put my finger on why. And I think this stuff that I'm talking about is part of the answer for me anyway. And what I mean there is that MVC sounds really good in theory. But somehow I always seem to find myself taking a model and shunting it through several stages of transformation on its way to the view. And I think this is why we have helpers and decorators and presenters and DCI and so on and so forth. So I'm starting to think that it might be better to model that model to view transformation directly as a kind of a composed or partially applied function or whatever you want to call it, where you pass in the model instance on the one end and it gets to the view as something else. Please don't take that as a recommendation, because just like Grug's shades, that's an untested idea, and I really don't want you falling off a cliff with it. Watch the movie. And it seems like, ironically, we're back to this, which is not the title of a book from the 1960s. It's a title of a book from 1976, which I haven't read because I'm still working on the stuff from the 60s. Well, actually, I don't think that's quite right. I think it's kind of like more we're here. Think Ruby, and think about what I said about fudging method calls with square brackets. Okay, I think I'm seriously out of time, but I still have chocolates left. So I can accept 3 answers for this. Turbo. Who said turbo? Anyone else? Come on. Has anybody seen this movie? Is King Candy is close enough, yeah. Hey, wait, you got 2. No. Give it to someone else, to a charity of your choice. Yeah, that's King Candy, who was originally Turbo, who got eaten by a bug and then hacked the bug from the inside. So he turned into this monstrosity, and that's actually him glitching between the sort of Turbo bug and the King Candy bug. And that basically brings me to the summary. But before we go there, I've done a whole talk on O, and I haven't mentioned a word, and I still have lots of chocolates. So the first person to tell me what word that normally crops up in OO talks I haven't mentioned Gets a chocolate. Close. Polymorphism. Who said polymorphism? One other one. What goes hand in hand with polymorphism? Oh, geez, come on, guys. I've got 3 chocolates left, not 5. What? Case statements everywhere. All right, fine, you get a chocolate. All right, and this brings me to my summary before I wrap up, and this might serve to remind you of something you might have wanted to ask and forgot. So, questions?
Where does nil fit into all of this?
Where is in what?
Where does nil fit
Where does nil fit in all of this? It's an object in Ruby, just like everything else. That's a good question. I hadn't thought of that. That'll be right next door to the one where I had rational equals the lambda. It does look like CoffeeScript, yeah. And prototypes, I don't think instances are callable either, because from what I understand, a prototype is basically a record of things, of which some of which are callable. I don't think there's any way to call. Yeah. More questions? Why? Because those parentheses drive me crazy. Because when I wasn't learning Lisp, we didn't have syntax highlighting editors, so figuring out those parentheses was... But yeah, I do actually have a more serious answer, but I'm very seriously out of time now. Okay, last one, wrapping up. Okay, I'll take 2 answers to this one. Come on. Uguay. Who said Uguay first? Did you say Uguay first? Okay. I would have gone for the cloud of peach blossoms previously known as Uguay, but anyway. You might have noticed that most of these pictures were of characters who maintained their identity while going through some kind of transformation. And I think this occurred to me as I was finishing the talk, and I didn't have time to go into it anymore, but I think the question of how to maintain identity whilst going through transformations is an interesting one, and if anybody has any ideas, I'd like to hear. And finally, some words of wisdom from Master Uguay. Now remember, the object that can be named is not the true object.
No come electro por la vida.